2011? 2013, wow, I'm asleep.
That's 2 years.
Been doing this for so long. Do you video guys get that? Oh no. So yes, this is 2013 in case you're watching back on YouTube land. So housekeeping, please sign up for lightning talks. We've only filled 5 of them and we need another 5 at least to make it a good hour's worth of lightning talks. So yeah, please do that. Other than that, I shall introduce our next speaker. It's always good when we get someone sort of outside of the free and open source software community to come and speak at this conference. If you have been in the iPhone and iOS development community, you'll recognise Mark from Cocoa Heads in Sydney, as well as being convener of the Swipe conference. Today he's going to be talking about embedding everything in everything for fun and profit. Please make Mark welcome.
I like to think of myself as a free and open source alumnus. If you search the Perl contributor commits really carefully, you'll find a very small number from me. So embedding everything in everything. Now, let's see if this is working. Excellent. Okay, so thankfully, you guys would all be with me on this. That you know, the days of one tool for every job is firmly been left in the 90s. So the whole concept of using the right tool for the right job is not something you have to sell anymore. It's sort of an established thing. But I'd like to take that another step further, and we still tend to pick maybe an overarching language for a project because it best suits that project. But then there's always little parts of that project that would be better at something else, or maybe even there's you've got this sort of schizophrenic project that would be great. One way it's painful, another, or this doesn't perform, or whatever. So my aim is combinatorial nirvana, embedding everything inside everything, or something that might get more traction on Hacker News is E-cubed. And before I get too stuck into it, a small admission. When I submitted my talk request to Chris, I thought the talks were an hour, not 25 minutes. So there's going to be probably a little more inspiration than actual code, but if I go quickly, we'll get to the real code. So what am I talking about embedding? So like I said, conceptually, this is from a real talk, by the way. Conceptually, the idea is, even within one program, even within one running application, there are different tasks that are better expressed, more conveniently expressed, more performance in different languages. So one obvious example is SQL, right? But that's not what I'm talking about. Not because it's not a good idea, but because you talk to SQL as a different process through some kind of inter-process communication. But what I'm talking about is having multiple languages inside of your process. One of the reasons why I want to do that is it seems really hard and really complex and the kind of thing that we would ignore. But it's not really that hard. So it's often the case in my experience that to simplify things you first have to be willing to enter into a higher level of complexity, and that sort of seems confusing. Mostly we're talking about von Neumann machines, right? Does anyone here program on something that's not a von Neumann or Harvard architecture computer? Sometimes, okay. They exist, but so that's von Neumann on the left there, and Robert Oppenheimer on the right. So for those of you who aren't sort of super familiar with it, let's have a quick look at the von Neumann machine. And this is basically what our computers are, right? We have memory, which has code and data, and of course in Harvard architecture it might be split, but let's talk about that. We have some sort of logic in our CPU. We have a set of registers, which are our super fast little discrete slots of memory, and we have an instruction pointer, which tells the processor what bit of code to execute next. And execution, basically all the logic part of our processor can do is it really does 3 kinds of things. It can do something with registers, might add them together, might move them around. It can do something with memory, move them in and out of registers, and it can do something with the instruction pointer. It can jump to another location. So the last one, the jump, is obviously the secret to us being able to call functions. So how functions are called, how they receive and return data is known as the calling convention. And it's a convention purely because, you know, ultimately you're running code on a CPU, you can do whatever you want. You can jump all around, you can stuff whatever you want in the registers. But if you're going to do that, then of course you need to document and understand very carefully exactly what's going where, and that's what you do in assembly programming. And fortunately we don't have to do that. So in most cases there's a standard calling convention described by a CPU vendor for that CPU, which in most cases is followed by the operating system, and in most cases is followed by the compiler of your particular language. So let's look at quickly at what that is. Okay, so here's another way of representing the von Neumann architecture. It's you can tell we're getting more serious because they now have square edges on the not round edges. So we've got the same things. We've got the registers, instruction pointer, and a code. And the calling convention is simply that we say, okay, here's a set of registers and here's what they're for. So we have, you know, maybe the first two arguments that get passed into our function. We have the return value, which is where we put the value when our function exits. And we have a stack pointer for, you know, a particular language of choice where the stack is stored. And there's obviously, you know, different complexities, but that's pretty much how it works. So our code that gets compiled down to machine language code, you come in and out of functions. There's a little bit of preamble that means that when your function runs, it can just get its arguments and it all sort of works. So when we look at it at this level, it really doesn't matter at all what language your code, whether it's, you know, interpreted or compiled. It doesn't matter how it works as long as it's sending, you know, as long as it's getting its argument from the same place and returning it from the same place, and it's obviously compiled to run on your particular architecture. It doesn't really matter. So there's kind of not really any logical complexity. It should all just work. And in fact, it's even easier than that because now if you didn't have the same calling convention between a bridge, you would have to kind of move stuff about with assembler. Now, fortunately, a whole heap of stuff we do is all based on C. So we don't need to worry about that because obviously the calling convention is the same. If you have a situation where you don't have everything that's, say, built in C, maybe using Java and something else, there's often some kind of foreign function interface like Java has J and I so that you can call out to C functions and vice versa. So that's just a little bit of background to hopefully sort of demystify what's going on under our you know, third generation language hoods. So let's look at an example of doing just this. So the examples I'm going to look at, I'm assuming I've got a C-based application, which, you know, might be a GUI, could be a web server, and I want to embed some kind of, you know, scripting language. So let's look at Ruby first. So assuming I've already linked in libruby and I've done some setup, I've got some C code here and I've got a bit of Ruby code here, and here's what I do. Now Ruby is purely OO for those of you who don't know much about Ruby. So this funny Ruby top self thing here is purely to get kind of the main namespace. So normally what you would do is you'd pass an object in there, but I've just defined something in the main namespace. So Ruby has this concept where to identify methods and you know, hash slots and things like that, they have this internal ID, which is kind of just, you can think of it like a string. But we need to convert from a string to that ID, and we need that because the RB funcall method takes an object or a namespace and this ID and some flags, and calls it. So this will actually work. This is all you need to do. And in this case, because the function has a side effect, I don't need to worry about returns or anything. And that will work. That's pretty easy, right? Perl. Same thing. We've linked with libperl. I don't know why I'm looking backwards because it's right here. And except it doesn't really work if I put my laser pointer here. But I'm sure you can read it. So we have call PV, which means, so there's a whole, you'll notice in anything, in any, especially scripting languages that are designed for embedding or vaguely designed for embedding, there's a whole bunch of ways to do the same thing. But, so in this case, call PV means we're passing in the name of a Perl subroutine as a string, as a C string, and gvoid there means we're calling in void context. We don't care about the return value. Again, same thing, that's all we have to do. Tickle. Does anyone here use Tickle? Good. So Tickle, the reason why I have these three, and I'll use these three a bit, is firstly because I have experience in embedding all these three inside other things. But also specifically, I like including Tickle because Tickle was intentionally designed for embedding. It was designed as a language to be embedded inside other things. Which is the reason why I came across it is it's embedded in a web server called AOL server, which used to be called Navi server, and now it's called something else. And that was made in like the 80s or 90s. And at the time was basically the only option if you wanted something that you could do, that you could embed a scripting language multi-threaded into a C process. So same thing here, to pass into Tickle evaluate object. Now, a Tickle is kind of, you could think of it like a functional programming language, for those of you that don't know it. Think of it like. So basically we're passing in it's prefix notation like Lisp or something. So in the case where we're just calling a function, all we do is pass in an object which is that function that gets byte compiled and stuff. Same thing, all pretty easy, right? So far we've made a C program that will call some other languages. Super easy. Except we haven't actually done anything apart from calling a function that has some side effects, which is not very interesting. So let's talk about something where we're going to, we're going to kind of stretch our friendship with the calling convention. We're going to send some arguments in and get some returns out. So again, Ruby. Okay, so now we're getting a little bit more complicated. We've got the same. This line up here is the same. We're getting our ID, which is the name of the function. And we're going to pass in an argument. So in Ruby, everything in terms of the C API, everything is this type value. Of course, in Ruby, like in a lot of scripting languages, you can kind of pretend that there aren't differences between types. But in fact, in the back end for performance, of course, there are numbers and whatnot. In fact, actually, sorry, in Ruby, of course, at the front end, there's all the different object types. But there's a single C type here, which is just sort of like an opaque object from our C point of view. But so we can make one of these Ruby objects values from RB-stru-new. I feel like it feels a bit like PHP, doesn't it? Everything's just this function. RB-stru-new for Dave, and we're going to call this function, and exactly like you would imagine with C, I get a return, which is an object. And I can call this, again, this Ruby API string value C-str to get a C string for that Ruby object, and it's all really easy. Now, things get a little bit harder when you have a language like Perl where we can have multiple return values. And in fact, the Perl C code to do the same thing is quite a lot more complicated. First of all, this DSP thing, kind of forget about that for the moment, but it's declaring a stack pointer variable. It's basically declaring this SP variable here. Now this enter and save temps, and you'll also see there's a corresponding down here, free temps and leave. That's exactly analogous inside Perl or Python or what have you of your curly braces giving you the context. So if I create within the enter and the save temps and the put back and the free temps and the leave, if I've created a Perl variable and it doesn't have any more reference counts, then it'll get freed there. So it's exactly like having my curly braces around it, which gives me a bit of safety that I can call a function and know that everything's going to get dealt with, cleaned up. Now, so a big difference here, and you'll see this in some other scripting languages in the C backends. The way that we interact with functions is we deal directly with a stack. So if you think of, so basically before we're calling a function, we're pushing values onto a stack. We call the function, and then we pop the results back off the stack. It's actually pretty easy. So all we're doing here is I'm pushing on a string. So this is kind of in one macro. Anything brown here is a macro. You'll see the C API has a lot of macros. I'm pushing on converting a C string to Perl, pushing it on the stack. This putback here is simply updating the stack pointer variable. I call the argument. Now, in terms of the Perl call v, the return value here tells me how many arguments were returned, because it could be variable, it could be a list. So again, I call this SP again, which again, all that's doing is simply updating this stack pointer variable. Now, I'm assuming that this value is only going to call 1. So here's something important, that when you're calling scripting languages from C, or really any other language from any other language, you need to be super careful about checking things like, you know, I've got the right number of return variables, because if I don't pop them all off the stack is now corrupted. So you're taking your life into hands a lot more doing this sort of stuff. And then again, I can pop a string off the stack and print it. Easy. Tickle, again, pretty similar. The tickle evaluate object v type of function takes a C array of arguments. So I'm really making a list here, which is the function name foo, and then the first function argument Dave. Remember, so it was a prefix notation. I call that. So it takes an argument as a C array, but similar to Perl, and it's a single return value, but it's kind of stored in a location, so we simply can get that as a C string or as whatever we want. Now again, here I know it's a string, but because it's a scripting language, it'll kind of convert it if it's something else. So at this point, you're like, whoa, this is getting a bit crazy. I mean, it's kind of straightforward, right? But especially when we're looking at the Perl stuff, which is what I do a lot of, it's a lot of stuff, and you know, it's easy to corrupt the stack by forgetting something or doing something in the wrong order, or the sort of things that you know, we're normally hidden from. So, but like I said, I've embedded those 3 languages inside, you know, reasonably significant systems. And it turns out that there's a pattern of approaching it that works certainly in the examples I've seen for any kind of embedding a language in another language. Now, one case I've dealt with was embedding Perl into a C host which already had tickle embedded and being able to pass them between. Once you've got it set up, it works surprisingly nicely. So the structure is this. You always have to do some kind of runtime interpreter setup, because interpreters have, you know, their state and runtime. You need sort of some functions for this bidirectional data transformation. So like I showed you, there's, you know, functions for converting to C strings and things, but that's pretty inconvenient to be doing all the time. So you sort of set up some code to do that for you. You have to do memory management yourself, of course. Make helpers for calling functions, which will also do the data transformation. If you're in an OO language, you can kind of wrap that into an OO base class. So again, you kind of don't have to keep doing it. And if you want to get smart, you can integrate the 2 runtimes. And if we get time, I'll show you a little bit of that. So that's cool, right? But at this point, you're starting to check your Twitter and think that PHP guy was actually talking some sense. Sorry. You had to expect to be the brunt, I think. So let's have a really quick digression and show you an actual demo. Now I'll just double check for the video people that we are still in. No, this one. Am I still in 1024 by 768? Okay, good. All right. So here's an actual app that is in development at the moment. That is an Objective-C app. Obviously, it's a Mac app, and it's running Perl under the hood. So here we have now, thanks to my client, Energy Frontier Services of Texas, for letting me use their data. So this is geological data, and there's, you know, hundreds of thousands, probably millions of data points under there. It's getting loaded by Perl, kind of munged by Perl, passed up to the Objective-C layer for pretty displaying. So now the stuff I've described sounds kind of slow, right? I mean, scripting languages are slow anyway, aren't they? Well, let's look. So here, let me just open up an inspector on this. So this red line here. First, let me pump up the weights so you can see what's going on the base one here, and I'll just kind of change some colors and things. And every single time that color is changing, I'm setting a property in an Objective-C object which is bridged automatically to a Perl object, sets that value, that updates something at the back end, a publish and subscribe message gets generated that triggers the Cocoa bindings framework, which is updating the color on that thing, and is then triggering the layer to redraw and doing an OpenGL redraw in the background. And it's pretty fast, right? And all this stuff here is simply bound to Perl properties on an actual data object. So what are the values for this? One value is that so for instance, I can look at this curve here, and I've got these filters now. I don't have any interesting ones loaded here, but let's see. I can add an average filter, and you can probably see what's happening there. I can reorder the filters, which won't make any difference in this case. Now, when I added that filter, what that did is that created a Perl object, stuck it into an array. That's all it did. And kind of like the Angular talk, everything notices that and refilters the data, updates that. So the great thing is that these filters here are Perl modules that are really a single method that's doing some maths on an array of points. So it's something that not only can the client write them, but actually the geologists can write can write their own plugins and things like that. Now I've lost my timer because I've gone back there. How long have I got?
Finish up soon.
Okay. So I was going to. No, I knew that I was going to run out of time, like I said. So let's super quick run through this. So the setup, you always have to do a little bit of setup for any embedded language, but there's a bit of a clanger here in the bottom part. The Ruby looks nice and small, but who can tell me what the problem is there? Where's the state variable? So that I can have multiple interpreters on different threads, or even in the same process. There is none, right? So the Ruby runtime uses global state, so you can't ever have more than one Ruby interpreter in a single process. You can with both Perl and with Tickle. That's sort of an example of sort of thing you need to look for. Now there's just a Perl example here. It looks a bit crazy, but again, in the pattern, you basically have this in every case. We have some sort of opaque piece of data coming in from another language, and you just end up with a big case statement, right? Big switch statement, right? We call some sort of API. If it's an array, then we iterate and make an array. If it's a number, we turn that into a number. It's again pretty straightforward. You do that once, you hide that complexity. Memory management, again, pretty easy. Now this is where Ruby is quite nice. Ruby is very slow for a couple of reasons. One is that the garbage collector scans the system heap, which means that you don't even have to memory manage your own C pointers to Ruby objects. It does that automatically, which is kind of cool. It's just slow. Helpers for calling functions, we kind of covered that. Now, object wrappers. Now, a few of you are barfing quietly into your little bath bags there. These are C macros. My take is that when the answer is C macros, you're asking all the right questions. Basically, what this is doing is code generation, right? So what that's letting us do is do things like here. So all of that crazy stuff we talked about, when I write an Objective-C class to wrap a Perl class, I'm simply saying synthesize a reassessor of type string. You call this Perl method on the object to get it, and here's the name of the Objective-C method. Sweet. And that's, and I won't cover that. And that's about it.
Any questions for Mark? Any questions?
So, are you looking at, interested in the idea of a language where you could pull that out a bit more automatically in order to generate the bindings? I'm thinking of like what glib's doing with their introspection stuff and lifting the GNOME libraries into different languages and stuff.
Yeah, so there's I haven't looked at that example. I mean, something that, there are things that will kind of try and automate some of that stuff for you. So Swig is one example, kind of at a low level, and there's other ones. So I kind of did it. So it's interesting doing it from the ground up. Firstly, because it's interesting to talk about, but also because I've just always found those things end up getting really messy, right? Because, so I've got some frameworks which the aim is that they'll get open source, but the reality is no one else will use them because they're kind of tweaked to how it works well for my project. And kind of what I wanted to get across is it's actually not that hard to kind of bootstrap it yourself from scratch. So
I've certainly had the swig issues when you're dealing
exactly.
with a bit more complicated too.
Exactly. Any other questions?
Any other questions for Mark? Excellent.
Have you looked at any of the tools that will create those bindings? For the ones I know are the ones in the file, and it produces everything that's needed for Haskell to call stuff from C. Brings
Yeah. So if you want to do so, actually, I didn't mention that. So usually when people are talking about kind of foreign function interfaces, you're kind of usually talking the other way around, right? You've got some kind of nice scripting language as your host, and you want to call into C. Now, so if you've got like a C library, you want to do that, then those things work kind of great. But yeah, when you want to do things in the reverse direction, those tools kind of don't work. And also they're kind of aimed at, yeah, you've got a library with a discrete set of functionality. I want to call stuff and get stuff back, rather than really having kind of a live interacting. Hybrid where I'm hiding the fact that this sort of current piece of mutated state is sort of part of my application, and developing them both, right? So this is specifically, I'm developing both ends of the thing. I'm not just trying to take a static library from somewhere and import that in. But if that's what you want to do, then those things work great.
Okay, I think that's all the time we have.
Cool.
So if everyone could please thank Mark Offlick for his talk.